Namaskar to Maths 1 lecture. Now let's move to our topic. The first topic is relation. So what is relation? Okay, so let's move to our definition. In relation, let's first see the definition of a Cartesian product. Okay, so Cartesian product of two non-empty set x and y. We are now familiar with the set. Okay, so there are two non-empty set x and y. Okay, so we are defining Cartesian product of these two sets, that is defined as the set of all possible ordered pair. Okay, all possible ordered pair such that x belongs to set x and y belongs to set y. Okay, and the Cartesian product is basically denoted with x cross y. Okay, so let's take the example as A is the set. Okay, here A is the set A comma B. Okay, and same here another set B, that is 1 comma 2 comma 3. Okay, so the Cartesian product, or that is the A cross B, is nothing but the ordered pair of x comma y. Ordered pair of x comma y means A with 1. Okay, A with 1 and A with 2 and A with 3. Similarly, B with 1, B with 2 and B with 3. Okay, so this is the Cartesian product. It is the ordered pairs. Okay, now let's understand the definition of binary relation, or we can say relation. Okay, so a relation between two sets x and y is a collection of ordered pairs containing one element from each set. Okay, what is this? A relation between two sets x and y. Okay, two sets x and y is nothing but a collection of ordered pair containing one element from each set. From every set we must have one element. Okay, in other words, a relation R is a subset of Cartesian product of x and y. Okay, this is the symbol of subset. Okay, so basically each relation must contain ordered pair containing one element from each set. Okay, each set से एक element होना चाहिए. Suppose A is A comma B is 1 comma 2 comma 3. Okay, so the relation R1 is A comma 1. Okay, B comma 2 and B comma 3. So we can see that we have one element from each set. Okay, same in R2 we have one element from each set. Same in R3 we have one element from each set. Okay, same in R4 we have one element from each set. Okay, now note that order of an element is important in a relation. Okay, in sets we does not follow the order. Okay, order was not important in set. Okay, but in relation the order is important, as a comma 1 is not equal to 1 comma a. Okay, now let's move toward the properties of relation. Okay, properties of relation. So the first property is reflexive relation. Okay, reflexive relation property. Let R be an binary relation on set S. Let's have something called set S as a 1 comma 2 comma 3 comma 4. Okay, so R is a binary relation on set S. Then R is said to be reflexive. Okay, the relation R is said to be reflexive if and only if for all x belongs to S. All x is nothing but the elements. Okay, so for all x belongs to this set S, the x comma x should belong to R. Okay, R is nothing but real number. Okay, so as we have this set S, so reflexive relation is nothing but the x comma x. Okay, that is the relation of element with itself. Okay, so the reflexive relation of this set 1 2 3 4, we can see that R1 is a relation that is 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 4. So every element has relation with itself. Okay, x comma x. So if the element is 1, x is 1, so 1 comma 1 is here, 2 comma 2 is here, so all the elements are here. Okay, so this is a reflexive relation. Okay, similarly, if we see in R3, 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, 4 comma 4 is there. Okay, so every element of x is there with its own with relation with itself. Okay, so all this is also a reflexive relation. Okay, now see this, here 1 comma 1 is here, 2 comma 2 is here, 4 comma 4 is here, but here 3 comma 3 is not present. Okay, but the requirement of reflexive relation is the that every element of this set S should have relation with itself. Okay, like every element has this relation x comma x. Okay, so as 3 comma 3 is not present here, so this is not a reflexive relation. Okay, so here R1 and R3 are reflexive relation, but R2 is not reflexive relation because 3 comma 3 is not present in R2. Okay, here R1 is also called identity relation. Okay, the relation in which the only elements present is the identity relation elements. Okay, that is only element present is x comma x. Okay, no other element than x comma x is present, then we can say that this is the identity relation. Okay, now let's move toward our next property, that is the symmetric relation. Okay, symmetric relation, we can see from the name, that is symmetry. Okay, so reverse should be equal to the original, then we say that this is what, a symmetry. Okay, so let R be an binary relation on set S. Same, we have the set S. Okay, 1 comma 2 comma 3 comma 4, then R is the relation. Okay, R is the relation of the set S, then R is said to be symmetric. R is said to be symmetric if and only if for every x comma y. Okay, for every x comma y there should exist a y comma x in R. Okay, if this exists, then we can say that this is the symmetric relation. Okay, so if x comma y is present, then its reverse should also be present in that relation, then we can say that this is what, symmetric. Okay, so here we can see that we have set S. Okay, and here x and y, the y belongs to set S. Okay, so element of x and y both are in set S. Okay, so now we can see that R1, in R1 we see that 1 2 is there, so 2 1 is also there. Okay, if x equals to 1 and y equals to 2, then xy is there, so yx is also there. Same 3 4 is there, then 4 3 is also there. Okay, and 2 2 is there, 2 2 is there, so if we take x equal to 2, y equals to 2, then xy is present, then yx is also this same element, that is 2 comma 2. Okay, y2 is also nothing but 2 comma 2 and xy is nothing but 2 comma 2. Okay, so every element uh, every element with its reverse is present in this relation. Okay, so this is a symmetric relation. Then we can see R2, 1 comma 2 is present, so 2 comma 1 is also present, 2 comma 3 is present, then 3 comma 2 is also present, and 4 comma 3 is present, and 3 comma 4 is also present. Okay, so every pair and its reverse is present here, so this is also a symmetric relation. Okay, now in R3 we can see that 2 comma 1 is present, so 1 comma 2 is also present. Okay, 2 comma 4 is present, 4 comma 2 is also present, 3 comma 4 is present, but no 4 comma 3 is present here. Okay, so it is not a symmetric relation. Okay, every element with its reverse should be present. Okay, no element there should be no element without its reverse. Okay, so this is called symmetric relation. Okay, I hope you got the point. Okay, Now let's move toward the third relation, third property, that is the transitive relation. Okay, transitive relation property. Okay, let R be a binary relation on set S. Again, that set 1 comma 2 comma 3 comma 4. Okay, then R is said to be transitive if and only if every pair of element x comma y, okay, every pair of element x comma y and y comma z, okay, and y comma z, y comma z belongs to R. Okay, if these two are present there, then there should be x comma z should also be present. That means x comma z should also be present there. Okay, so we can see that now. Let's take an example as we have our subset S. Okay, so here we can see that, oh, sorry, we can see that S is a set 1 comma 2 comma 3. Okay, so we can see that in R1, R1 is a relation. So here 1 comma 2 is present. Okay, 1 comma 2, that is x comma y is present. Okay, x is equal to 1 and y equals to 2. Okay, and y comma z is present, so y equals to 2 and z equals to 3. Then there should also, if there x comma z is present, if there x comma z is present, then it is known as transitive relation. So it is the transitive relation. Now we can see the R3. Okay, let's see first see R4. Okay, R4, 2 comma 4 is present, 2 comma 4 is present. So let's find 4 comma 1 is present, 4 comma 1 is present. So 2 comma 1, that is x comma z, should also be present here. So here 2 comma z is also present. Okay, so and we can see one more thing, 1 comma 2 is here, 1 comma 2 is here, 2 comma 1 is here, 2 comma 1 is here. So there should 1 comma 1 should also be here. So we have 1 comma 1 is also here. Okay, uh I guess every thing is there. Okay, 1 comma 4 is there, 4 comma 1 is there, so 1 comma 1 is also there. So every element follow these three things. Okay, every element follow these three things. So we can see that we can say that this is also a transitive relation. Okay, now we can see here 1 comma 2 is there, 2 comma 1 is there, so 1 comma 1 is also there. Okay, and 2 comma 3 is there, so it is not a transitive relation. Okay, now we talk about R2. Okay, R2 and R3. We can see here x comma y is there. Okay, but there is no y comma x. Okay, y comma z. Okay, there is no y comma z, so we are not able to make condition. Okay, we are not able to make our condition. So in that case, when we are not able to make our condition, this will be transitive relation. Okay, that will be transitive relation if we are not able to make a single condition. Okay, here we have one condition. Okay, we had one condition fulfilled, so this element left alone, so this is not a transitive relation. But here we can't able to form a single relation, so this is transitive relation. Okay, this will be transitive relation. Same here, 1 comma 3 is present, but 3 comma something is not present, 3 comma z is not present. Same 1 comma 4 is present, but there is nothing called 4 comma something z is present. Okay, so when these are not present, then we can say that it is also a transitive relation, because we are not able to form a single relation. If Let's me write this thing here. uh, if we are not able to form a condition single condition, then it will be transitive relation. Okay, so then it will be transitive relation. Okay, now let's move toward our next topic, that is fourth relation, that is equivalence relation. Okay, if a relation is reflexive, okay, symmetric and transitive, if both three properties are there, okay, if a relation satisfied both three properties, then this will be that will relation will be called equivalence relation. Okay, here you can see that we have set s as 1 comma 2 comma 3 comma 4, and we have proved all the things on this set. Okay, this 1 comma 1 2 comma 2 3 comma 3 and this whole everything you can check for all the three relation. This set will satisfy all the three relations. Okay, so we can say that this is the equivalence relation. Okay, now let's move toward our next topic, that is function. Okay, a function is a relation. Function is what? A relation. It is nothing but a relation. Okay, in which each element in set x, okay, in set x is mapped or paired, okay, paired, okay, with exactly one element in set y. Okay, so if we have anything like a 1 comma 2 in set x, okay, 1 comma 2 in set x, and y is 3 comma 4, if every element is paired or mapped to a single element in y, okay, every element of x is mapped to a single element in y, then we will say that that is a function. Every element of x should be mapped with a single element, exactly one element in set y. Okay, so in a function there should not be two pairs with the same first element. Okay, same first element should not have should not have two pairs. Okay, in a function a particular input is given to a particular output. Okay, in a function, what if for a very particular input, we will get a very particular output. Okay, so a function f of x belongs to y denotes that f is a function. Okay, this symbol says us that this is a function. Okay, f is a function from set x to set y. Okay, this means that the f is a function from set x to set y. Okay, where x is the domain, and y is the codomain. uh let's see what is domain and codomain. So domain of f is basically set of all input values of x. Okay, so if x has, let's say, 5 elements, okay, so all the elements of x is known as its domain. Okay, the value which we put in the function to get the output, okay, that value is basically domain. Okay, now what is codomain? Codomain is the set of all possible output values, okay, or we can say set y. Okay, so this is basically all the possible values which can be possible, okay, which can be possible after putting the domain x. Okay, that is known as codomain. Okay, now range range of a function f is nothing but the values of y. Okay, all the values of y for which when we put the value of x in the function, we will get the value of y. So the range is nothing but the all the values, okay, all the values which we get after putting the domain in the function. Okay, let's not get confused with it. Let's see an example. Okay, so here is an example which is telling basically which is function or which is not a function. Okay, so here you can see that this is a set x. Okay, this is set x and this is set y. Okay, here you can see that the element of set x is basically mapped to a single element in y. Okay, so here one is mapped to b, Okay, 2 is mapped to C, 3 is mapped to A, and 4 is mapped to C. Okay, so this is what called a function. Every element of X is mapped to a single element in Y. Okay, every element of X is mapped to a single element in Y. Okay, and here um, these are called basically domains. These are nothing but domains. Okay, if we have a function, something defined as X belongs to Y, then these are basically, the X is basically the domain. Okay, this Y is basically the codomain. Okay, this Y is basically the codomain, and these three, okay, these three is basically range. Okay, these are the possible values which come. Okay, codomain is basically all these. Okay, because the domain X can take all these values. Okay, all these values, but the actual values are what? Range. Okay, the actual values are range. Here you can see that 1 is mapped to B, 2 is mapped to C, 3 is mapped to D, and 4 is mapped to C, and also 4 is mapped to D. So one element has two different outputs. Okay, is basically one element of X is mapped to two different elements of Y. Okay, so this is not a function. Okay, I hope you are clear with the function. Okay, now let's move toward our next topic, that is the types of function. Okay, we have read the function. Now function has its type. Function has three types. Okay, first is injective function. If each element in set X is mapped to a distinct element in set Y. Okay, if every element in set X is mapped to a distinct element, okay, different elements, not the same, okay, not the same, but the different, okay, distinct element, then it is known as injective function. Okay, then it is known as injective function. Next, surjective function. If the range is equal to codomain, if the range that means this range is equal to codomain. Okay, if the range is if in this case, if the range will be A, B, C, and D2, then the range is equal to codomain. Okay, then the range is equal to codomain, then we call that function as surjective function. Okay, and we call this as surjective function. Okay, now what is the bijective? If the function is both injective and surjective, if it is both injective and surjective, then we will call it as bijective function. Okay, and we will call it as bijective function. Okay, thank you. Do like, share, and subscribe if you like my video. Thank you.